choose the Q and then choose the next action. Or Sarsa or expected environment. If the environment is safe path, so that's part. Not policy. Avoid action. Region marked the cliff. Stepping into the cliff incurs a reward of -100. This example of cliff walking, so reward is -1 on all transitions except those into the region marked the cliff. Stepping into the cliff incurs a reward of -100 and sends the agent back to the start. So Sarsa will learn the safe path, whereas Q-learning will learn the dangerous path, which is optimal because it's shorter. But because occasionally it falls into the cliff because of the epsilon greedy action selection. So Sarsa takes the action selection into account because it's an on-policy algorithm, so it learns the safer but longer path through the upper part of the grid. So during the episodes, Sarsa will have a higher sum of rewards during the online learning. Sarsa has a higher average reward. However, if you gradually reduce epsilon to 0, approaching a greedy policy, then both methods will converge asymptotically to the optimal policy. So if epsilon is 0, then the lower path is indeed optimal because you never fall into the cliff. Well, this is assuming a deterministic environment. If the environment is not stochastic, then still Q-learning may this lower policy may not be very good. Yeah, this is environment is deterministic. Yeah, only action selection is stochastic. So this is textbook's chapter 8, planning and scheduling. So so the model we talked about model-based and model-free. What is the model exactly? So one type of model is sample models. So it produces just one of possible outcomes sampled according to the probabilities. It can approximate probability of each outcome, requires a little memory, or distribution models, which produces the complete probability description of all possible outcomes. Probability distribution. So it can compute exact probability of each expected outcome and requires more memory for storage. So here, this is describing the possible outcomes for 2 coin flips. So either model can be used for state space planning, dynamic programming approaches, such as value iteration and policy iteration. So when we discussed MDP before, we were discussing the distribution models. but sample models are also fine. For random sample, so for the Q planning, so the planning uses simulated imagined experience generated by a model, and learning uses real experience generated by the environment. They can be combined. Agent uses planning to learn that moving right and falling off the cliff is bad, so it avoids the moving right action without actually doing it. So you are performing the actions, and based on a Q-learning or Sarsa or expected Sarsa, you are doing one update after every action. But with Q planning, you are thinking in your head. The agent is thinking silently without taking any action. What if I take an action here? What will happen? What if I take action there? So it's performing this planning in its head. So this one-step tabular Q planning assumes first you have this sample model, this kind of sample model. Assuming you have this model, and then you send the state action to the model and get a next reward and sample next state. And then you apply this Q-learning update. Notice that this particular A is an imagined action, not an actual action. So this is Dyna algorithm, which unifies the direct Q-learning with direct RL with real experiences. And then it has indirect RL, that is model learning followed by Q planning. So real experience is used to improve the model to make it more accurately match the real environment, and which is then used for planning. So model learning. So the difference from the Q-learning is the red part. The other part is the same as Q-learning. So the actual steps are to do a model learning. So assumes deterministic environment after every transition. It records in this table entry for ST80 the prediction that RT plus 1, ST plus 1 will deterministically follow. If the model is queried with a state action pair that has been experienced before, it simply does a table lookup and returns the last observed next state and next reward as its prediction. So that's the model, a simple table lookup. And during planning, the Q planning algorithm randomly samples from state action pairs that has previously been experienced. So real experience builds a model and uses simulated experience to plan updates. And on the other hand, for direct RL update, you learn from real experience as before. So you have two update branches for the same value function. So here's an example of this maze environment. So the agent initially has a random policy, and it stumbles around until it reaches the goal. Afterwards, only this one state policy is updated, its Q value is updated, the other Q values all stay 0. So all the experience before reaching G is discarded in normal Q learning. But for Dyna-Q, it keeps track all the previously visited states and actions and rewards, and learns a model by keeping track of them. So and makes better use of environment interactions. So for future episodes, for Q learning, this Q will gradually propagate back. So the next episode, when it ends here, it'll update this guy. The next episode, it will update this guy. So the propagation of Q is really very slow. But for Dyna, it uses the learned model to plan better policies for all previously visited states. So by the end of third episode, a complete optimal policy has been found. So the n here is 50, and here is the number of planning steps within the Q planning. So here's the example with n equals 100. So in the first episode, it takes 184 actions for the agent to reach the end goal by a random policy. And then in the next, before you take the next action, 184, and to the 185th action, you do 100 steps of planning in the middle. And the planning will update these two Q values, although the agent is just moved from here to here. So that's the actual action. But in its head, it's doing simulations and performing Q planning based on learned models. So it updated these two Q values. Despite that, it has never moved close to these two positions. And at action 187, there's two more actions taken. So it moved here and here. But two steps, there are 200 more planned steps. So it learned more Q values by planning, and so on. So even though the agent is still moving around in this corner, it never left this corner. The policies are being improved. The Q values, which determine the policy, are being improved by the planning steps over here. So that's the Dyna algorithm to combine planning with learning to make better use of past experiences. And for prioritized sweeping, this is so in the original Dyna algorithm, we say that we randomly choose previously observed state and action and do Q learning based on that. But that's not a very good strategy because obviously, if you're performing Q updates over here, over here, over here, they're not going to help you much because the changed values are over here. So only these have non-zero Q values. So you should prioritize the states close to these goal state and nearby states. So by prioritizing the state action pair prioritized by the size of the change. So that's the insert with this guy, priority is determined by the size of the expected change, and then pop out the highest priority in the queue to preferentially update these entries. So for the maze example, you work backward from the goal state by giving higher priority to states leading to the goal state than those far away from it. That is, you try to prioritize these states over these states. So based on prioritized sweeping, you can get more efficient learning. So what if your model is inaccurate? So what if suddenly there's an obstacle arriving in the middle during your learning? It's okay. So the models may be incorrect because the environment is stochastic and or a limited number of samples have been observed, or because we are using function approximation, or the environment has just changed. So then the planning process will compute a suboptimal policy based on previously learned incorrect model. But when you actually encounter this obstacle in the real experience, the error will be corrected. So Dyna-Q Plus essentially adds exploration bonus to encourage exploration. So it adds this kappa square root tau. Tau is the number of the transition has not been tried in tau. So the longer a transition has not been tried, the more likely that it's stale and may be out of date. So it may have changed. So by adding this exploration bonus, it preferentially explores the transitions that have not been visited for a long time. So here, in the reward, we add additional exploration bonus. And with the Dyna-Q Plus, the cumulative reward, so this environment suddenly changes as time step 1,000. Originally, the optimal path is here. After the change, the optimal path is here. It's like this. So so Dyna and Dyna-Q Plus will realize this. So there's a flat area where this is perhaps actions that has not encountered the differences. The differences lie in two positions, this position and this position. So if your movement, your actions have not encountered one of these two positions, then it's not going to learn, but eventually you'll learn these two positions. And Dyna-Q Plus performs better. So this is, if you recall from the what's the multi-armed bandit example where you had exploration bonus for the arm that you haven't pulled for a long time. So this is similar to encourage you to explore the unknown. So this is a summary of the tabular methods. So if you have a model, then we use the MDP planning methods, policy iteration, value iteration. But if we don't have a model, then we either learn a model first by doing Dyna or Q planning, or we do completely model free. And if we can do a learn per episode on the right with Monte Carlo methods, Monte Carlo can either do evaluation only or do control to improve the policy. Or if it's a if we want to learn per time step, then we use Sarsa or TD or Q learning. So and then TD can only be used for policy evaluation, not control, because it evaluates the V, not Q, and you cannot go from V to Q without a model. Whereas Sarsa and Q learning, they learn the Q directly, so you can use them to get the greedy policy by argmax. So any questions on this value-based IR? So I actually have two more lectures. One is on function approximation. One is on policy-based IR. So I think I'll keep going, perhaps for some time. And let me, so let me set the exam scope to be lectures 1 to 10. So lecture 11 will. So let's go and start lecture 10, function approximation. So you can, instead of tabular methods, you can use a function to approximate either the V state value function or the Q, the action value function. So for the Q, you can either use A as an input, or you can compute all possible Q functions for all possible actions. If you use neural networks, it corresponds to having A as the input and producing one QSA, or producing all QSAs for all possible A's. So I think Carlo mentioned this before. Because you need all the QAIs for all A's for computing the argmax A, the greedy policy. So the latter approach is predominant in these days. So the mean squared error, I mentioned this before in the imitation learning lecture, but just to reiterate, so suppose we have a real value function v pi, the blue curve, and we use a linear function to approximate the v pi. V hat is the estimated value function. So we want to minimize the value error, which is expectation over with expectation under policy pi for the squared difference between v pi and v hat. So expectation is taking a sum of all the states with the weighting factor mu as probability distribution of state S when following policy pi. And sum over all S of mu S is equal to 1. So this is just the definition of expectation. So we want to minimize this value error. We can use a gradient descent. So here the x-axis corresponds to the weight vector W. So we typically use the bold letter to represent a vector, and a non-bold letter to represent a scalar. So in general, it should be a bold vector, especially for neural networks. There may be millions of weights in a deep neural network. But the cost function is a scalar, a loss. And every time you follow the gradient, gradient is a symbol here, represents a vector of partial j over partial w1, partial j over partial w2. Okay, so the w1, w2s are not vectors. These are elements. These are elements of the vector, weight vector. And the alpha is the step size parameter. Typically, it's gradually reduced as you run the gradient descent. So, so here's the gradient descent for minimizing the mean squared value error we saw before. First, we can take the gradient operator inside the sum, because it's taking gradient with regard to the weight vector W. So it's not, the sum over mu is not a function of W. So you can take it inside. And then you can gradient of the square is 2 times this value, and then gradient over the v hat. That's just the chain rule. And then with the weight update, you have this formula here. So this is not practical to evaluate for a large number of states. We do this by sampling again. So we replace this expectation by sampling to have a stochastic gradient descent. So at every step, you update W based on a single new state and its value v pi. So now notice, first we remove this guy because we're evaluating the expectation by sampling. Second, we now have the capital ST instead of the small s. This indicates a particular sample of state at time t, whereas small s is a random variable. So that's a stochastic gradient descent. So for gradient Monte Carlo, you simply use the Monte Carlo target G, that's the return, as unbiased estimate of the v pi. And at every step, you update the W based on using GT to replace the ground truth v pi st. Remember, GT is a return from current time step until the end of the episode. So that's gradient Monte Carlo, and also we can use TD. So TD uses a parameterized value function to approximate the true value function v pi, and you're trying to learn a mapping from a state to the target value, which is next step reward plus next state value times gamma. So now the target is dependent on W. It's non-IID, independent and identically distributed. So I mentioned this before during imitation learning. So this compared to supervised learning, say you're mapping from pictures to labels, and you have a fixed set of training data set. X may be an image, Y may be a label of a cat or dog, and these are not affected by your weights. So they're there, they're static. Whereas for TD, your target is changing as you update W. So it's really a moving target. So for TD, you are using the TD target as a biased estimate of V pi, as opposed to the G for Monte Carlo, which is unbiased. So now, if you're taking the gradient of this squared error in a sampling approach, a particular sample of ST plus 1 and RT plus 1, you cannot simply take the gradient inside and do this, because this term here is dependent on W. That's the non-IID part. So this gradient is not equal to 0. However, we pretend it's 0 and simply do the call it a semi-gradient. So yeah, this is the red. So if you remember the gradient Monte Carlo, stochastic gradient. So at this point, when you are from here to here, you can V pi is not dependent on W. That's the ground truth value function. And taking gradient over with regard to W does not affect V pi. So you can just take it outside and move the gradient inside. But here, this guy, the target here, is dependent on W. So we cannot move it inside, strictly speaking. So there are research that does the gradient TD. You can take the gradient on both terms with the chain rule, and there are some results. But this more common approach is semi-gradient. That is, you pretend this first one does not depend on W, even though it does, and just take gradient over the last term. So semi-gradient, because it's not a true gradient, it may not converge to the local minimum but it converges faster than gradient Monte Carlo due to more frequent update per time step instead of per episode, and less noisy updates, less variance. So the semi-gradient TD solution may be stuck in here, so it may not reach the even the local minimum. So with a linear function approximation, so we're not yet discussing neural networks, which is a non-linear function. Let's first try linear function first. So the value function is a product of weight and the feature vector. So the transpose notation just says it's a horizontal laid out vector. Without a transpose, it's a vertically laid out vector. So if you have a feature vector of size 2, then this value function is this w1x1 plus w2x2. So that's the same state with two features, and taking a derivative, taking a gradient on W gives you this. It simply returns the vector x. So semi-gradient with linear function approximation simply has x on the right-hand side. That's the feature vector. Whereas before, we had this gradient operator applied to v hat. But here, v hat is a product of two terms. So it's simply x. So it's step size alpha times TD error times feature value.
May I ask
the vector notation for both W and X. So did someone ask a question?
Yes, this last slide, linear function approximation, is this particular for the semi gradient descent, or is it general?
Linear function approximation is used for simpler cases. For realistic large systems, you must use a nonlinear function like a neural network. So this semi-gradient is for here it's for the linear function approximation, where you have to when you take a derivative, you're ignoring the target when you take a derivative. Ignoring that the target is a function of W, as well as the function being estimated. So the target is a moving target. So you must, if you want to do the rigorous derivative, you must perform a chain rule and write out both terms. But in here, we're throwing away one term of derivative and only keeping the derivative with regard to the second term.
Yes,
so
I understand it, but it's more like my question is regarding this linear function approximation. Is it applied still on the semi-gradient descent, or is it combined with it, or is just a general case which doesn't actually need semi-gradient descent?
So maybe you're asking, if you use a deep neural network, do we still need semi-gradient TD?
No, it's not. It's just like, is this just next step? I mean, we already applied semi-gradient descent, and then next step is actually approximation linear function, or is this actually avoiding need for semi-gradient gradient descent?
No, this is because we adopted the linear function approximation, and then we use the semi-gradient descent to simplify the derivative.
Oh, okay, now I understand. So it's like semi-gradient descent is anyhow applied afterwards. So it's just this is simplification before.
Yes. Yes.
Thank you.
Okay.
So there's a theorem that relates linear TD's fixed point and minimum of value error, which is less than or equal to 1 minus gamma. So it's a non-trivial theorem. So if gamma is large, that is, you're looking a long time into the horizon, then error of TD may be very large. If gamma is very small, you have a very short nearsighted view, then the value error of TD can be very close to the true minimum.
So let me just to be more complete. So semi-gradient TD is used for pretty much any function approximation of the value function. So for linear, it's shown on the slide. But if you use a neural network to approximate the value function, you still use semi-gradient TD. That is, the V here is a deep neural network. So you still have the first term as a TD error, and the second term you take a derivative with respect to the weight, the neural network parameters. So semi-gradient is used whenever you use function approximation for your value function.
So tabular TD is a special case of linear TD by using a one-hot encoding of states with 1 for the ith element and 0 for all others. So for example, if you have two states S1, S2, you just have two features to recover the tabular TD case. One feature is 1, 0. Another feature is for S2. The feature for S1 is a vector of 1, 0. Feature for S2 is a vector of 0, 1. And then the value function for S1 by the definition is equal to W1. A value function for S2 is equal to W2. So the features simply pick out the corresponding weight for that state. So it assigns a value to each individual state. That's the tabular TD. So if you work out the semi-gradient TD, it's same as tabular TD, except using the value function form instead of the table form. But the value function form we saw before is just the particular weight, so it's the same. So tabular Monte Carlo is also a special case of linear gradient Monte Carlo. So in books chapter 10, it talks about on-policy control with approximation. We saw this figure before, generalized policy iteration for tabular setting, updating the Q for each SA, each iteration, based on a table. But for function approximation setting, it's essentially the same, except you use QW, which is really the Q hat here, as a function approximation instead of a table, and you update the W parameters, which affect the Q hat in each iteration. Other things are all the same. So for the updated equations, if you have recall Sarsa and semi-gradient Sarsa with function approximation, simply replaces the capital Q, the tabular version of a Q value for state action, with the Q hat, the function approximation for it. And you have, I should also highlight the difference is you also have the gradient term on the right, which is extra compared to the tabular setting. And for expected Sarsa, same, similar. Q-learning, similar. Yeah, just a simple replacement. And you can use linear function approximation as Q functions. So W times X SA instead of W times XS. So you can replace the gradient term with X with the linear function approximation. So that's the end of the short chapter on function approximation. Any questions?
Did you upload the slides?
I have
Lecture
10.
Yes, it is now part of lecture 7.2.
Okay.
At the very end.
Okay.
Yeah. So yeah, we have finished the function approximation part. Now the next lecture is policy-based IR. So let me see. Let's take a few minutes break. Maybe 5 minutes. So this is the last chapter of our course. So because this lecture has a little bit math, quite a bit of math in it. So the exam will cover up to lecture 7.2. That is, we're not going to cover this chapter in the exam. This is for entertainment only. So this is the picture for policy-based IR, where you directly learn a policy function for each state and map the state into an action, either a deterministic or probabilistic action choice. So as opposed to the value-based IR, where you learn the value functions first, and then do argmax on the Q value function to get the action. So the policy-based IR is more direct. So this is the overall picture. So we covered value-based IR. And now we're covering the policy-based IR with no value function. We're learning the policy directly. And there's a hybrid method called Actor-Critic, which means that the agent learns both the value function and the policy function simultaneously. So the policy-based IR has the benefits, including that it's effective in high-dimensional or continuous action spaces. So value-based IR is only applicable to discrete action space. Because if you have to do a argmax on the action, so it's not it's not really feasible to take an argmax for continuous action. And also it's inefficient to discretize the continuous actions for high-dimensional action space. So if you have action space of many dimensions, then discretization will result in a lot of actions. So it's grows, the number of actions grows exponentially with the number of dimensions. So taking an argmax may be too expensive for high-dimensional actions. But in our examples in this course, we have pretty low dimensional actions, maybe 2 choices going left or right, maybe 4 choices going up or down, left or right. So there are applications that maybe the action space is high dimensional. And also another benefit is that you can learn stochastic policies. So whereas value-based IR learns a deterministic policy, or if you add epsilon greedy to it, it learns a near deterministic policy. And our policy typically converges faster than value functions. As we saw before, starting from NDP planning, the policy already converges faster. So in general, value functions may continually change across iterations, but the policy induced by the value function after you take argmax may converge much faster. So you don't really have to wait for the value functions to converge, because all you really care about are the policies, not really the exact values of the value functions. So disadvantages are that it typically converges to a local rather than a global optimum, because you're taking a gradient descent, and also evaluating a policy is typically inefficient and high variance. So we'll see this later. So here's a simple example of a mountain car, which is a very common hello world type of example for reinforcement learning. So this is a little vehicle. that does not have enough power to drive it out of the valley. So when it goes up, it comes down. So it doesn't have enough horsepower. So the problem formulation is to decide on a policy of velocity versus position, and so that you can get out of the valley and reach this point. So maybe you have the first try, you come in this trajectory. The second try, you may go further. Third try, you may go further, and eventually you can reach your goal if you accumulate enough momentum. So here's the value function landscape. So you can see that for every position and velocity combination, there's a value for that point in the state space. So the state is a tuple consisting of a position and velocity. And the action, you have two choices: move, accelerate left or accelerate right. So for this is a simple policy on the right that works very well. So just accelerate in the direction of current velocity. So if the current velocity is moving right, you just accelerate to the right. If the current velocity is to the left, you'll accelerate to the left. So it turns out this simple policy always adds momentum to the vehicle, so that it will accumulate momentum more efficiently and get up to the goal pretty fast. So this is example just shows you that it's not necessary to learn this very complex value function landscape. You can design a pretty simple policy just like that. So that's why a policy, learning a policy is often simpler, easier, and converges faster than learning a value function. So this contrasts learning a function approximation for action value. So you have state action pair, and you learn a function approximation parameterized by W. And then you can derive a deterministic policy by taking an argmax on the learned Q value function. So you may add epsilon greedy during training. So typically epsilon greedy is only for training, for the training stage. Sometimes you may want to add epsilon greedy even during the testing for the trained agent. But generally we don't do that. Generally the agent just follows the deterministic policy at runtime for Q learning. So for policy-based IR, it learns a function approximation for stochastic policy, pi, which denotes a probability distribution. So pi a, given S and theta, is the probability that action A is taken in state S, parameterized by theta. So the actual action taken is sampled from the probability distribution. And the actual action A, capital A, is sampled. This little tilde indicates sampling from a probability distribution. So the probability must be non-negative. So every pi must be greater than or equal to 0. And also probability is sum to 1. So very, very obvious. So one very common choice for the policy probability distribution is the softmax. So softmax has its form of exponential. The H, which is action preference, if you use a deep neural network, it's legit. If you use a linear function approximation, it's just a linear function outcome for the legit. So for the activation just before the nonlinear operator, the softmax layer. So here it shows the mapping from action preferences, the legit, to the softmax through the softmax operator to the probability of taking each action. So a bad action with very negative action preference H will be very unlikely to be selected due to the exponential operator. So action probabilities change smoothly as a function of the H. So for epsilon greedy, you select the greedy action argmax A of the QSA with probability 1 minus epsilon plus this epsilon divided by the number of actions. We saw this before. So this method of choosing a action probabilistically has some disadvantages. One is that there's no distinction between policies that are not the optimal one. So a bad action with very low Q value will be selected with equal probability as all the other non-optimal policies. So here, the three non-optimal policy action choices, even though they have very different Q values, they have the same probability of being taken based on epsilon greedy, which is not really reasonable. And also, action probabilities may change dramatically for an arbitrarily small change in Q, if that change results in a different optimal action. So suppose after some update to the Q function, this guy grows to be higher than the one on the left, then suddenly this action probability will suddenly grow very large, and this action probability will suddenly grow very small, be reduced to be very small. So the change in the action probabilities can be discontinuous. So these are both of these drawbacks are avoided in the softmax formulation of the policy. So there are benefits with taking a stochastic policy versus a deterministic policy. So for example, the two-player game of rock, paper, scissors. Scissors beat paper, paper beats rock, and rock beats scissors. For this kind of iterative game, where each opponent takes one action followed by the other opponent, a deterministic policy is easily exploited by the opponent. And the uniform random policy, where you select each of the three actions with a 33% probability, is optimal and achieves the Nash equilibrium. So another example is the alias the grid work example. To illustrate the benefits of having a stochastic policy. So here's the environment. It has three terminal states. Two is high positive, two with one with high positive reward, and two with a high negative reward. So this is the positive reward. And these two are the negative rewards. So it's a partially observable MDP, palm DP, in that the agent cannot observe its position directly. It can only observe features of the following form. So for all directions, north, east, south, and west, so it can detect if there's a wall to any direction. So with a LiDAR or radar, but nothing else. So here, this 1 indicates it's an indicator function. So 1x is 1 if x is true. Therefore, the agent cannot differentiate between the two gray states. So in the two gray states, there's a wall to the north, to the west, and to the east. So, so these two states are identical based on the limited sensing capability of the agent. So the value-based RL learns a deterministic policy, assuming we're not using epsilon greedy during the after training for the train agent. So the policy is fully deterministic by taking an argmax of the Q value function, which is a function approximation. Could be a neural network, could be a linear function, I don't care. So the policy-based RL learns a stochastic policy, which is a mapping from the state, first with perhaps a linear function or neural network, then a softmax operator, and then it maps in the probability of taking each action. So here on the left, it shows the optimal deterministic policy. So the actions in these states, in this state, it's pretty obvious. It should go right. So in this state, it's pretty obvious. Go left. In this state, it should go down to get the reward. So these three states have obvious, correct, optimal actions, but these two states are more problematic. So which way do you turn? So ideally, you wanna move into the east in this state and move to the west in this state. So that's the ideal condition. But you cannot do that with your limited sensing capability because you don't know exactly which of the gray states you are in. You can only detect walls on 3 directions, but you don't know whether you are in the left gray state or right gray state. That's a palm DP, not a MDP. So you must have the same policy in these positions based on the policy mapping function. So we can either move west in both of the gray states as shown in the red arrows, or move east in both of the gray states. So if you adopt either of these two choices, so in this picture, we take the west option. Then the agent can get stuck and never get to the money. So from the right, this is okay. You get to the money, but from the left, you just go around in these two locations. It's stuck in an infinite loop. So so for the optimal stochastic policy, you can randomly choose east or west in the gray states with 50% chance each. Once you detect, I'm sorry, I didn't say they right. The walls are to the north and south. So you cannot move because you're blocked by the walls. But on the east and west in these gray states, there are no walls. You can move. So if you have walls to the north and south, you're in one of the gray states. If you have walls to the north and west, you're in the left corner state. Similarly, to the right corner state. If you have only a wall to the north, you're in the center state. So these three states have no ambiguity.
Excuse me?
Yes?
Actually, you are using now this gray color just to indicate that that they have walls on different sides, but basically they have no other difference with other cells.
Well, from the they have the same wall configuration. That is, the wall to the north and south is common to for both of the gray states.
Yes, I understand, but it's just like in this case, you are using the gray color just to indicate few things, but it's actually for the model, it's have no difference.
Or from the POM-DP perspective, these two states are identical, but from an MDP perspective, they are different. So if you had a GPS, you know the exact position, then it's MDP. It's no longer a POM-DP. Then you can distinguish between these two gray states, and you can design an optimal policy, like I said before. That is to go right here and go left here. But for POM-DP, you don't have the full knowledge of your position. You can only tell that you're in one of the gray states, but not exactly which one. So in this POM-DP setting, the agent, the best policy is really to take a random policy, just to have a 50% chance of moving left or right in the gray states, and then it's likely to reach the goal state quickly. So if you use the other alternative for making the policy stochastic by the epsilon greedy method, if you add that on top of the optimal deterministic policy, so in every state, you have a small chance of choosing some other action other than that's different from the arrow direction, the optimal direction. Then it kind of works, but it doesn't really work because the agent may get into one of the two bad states, since each non-optimal action is given equal probability in every state. That's the definition of epsilon greedy. That is, the epsilon is common to all the states. You cannot say that in one state have one small epsilon, in another state have a bigger epsilon. No, the epsilon is uniform across all states. So therefore, you have a chance of getting into the bad state. But with this, maybe a softmax, maybe some other method, but of defining a stochastic policy, you can make it non-deterministic. So that you can avoid the bad states completely, because in this corner states, the policy is fully deterministic, but in the gray states, you are stochastic. So any questions?
Just one comment. I mean, for the corner cases, if you just define the probability to move right is 100%, then it is still a stochastic policy, but it's just there's just one state, just like one possible outcome with 100% probability.
Oh yes, in fact, that's exactly what the pi does. So the pi for move east and wall to the north and west, that's the left corner, is equal to 100%, and the other pi for moving west is equal to 0%, and moving south is equal to 0%. Yeah, that's right. So if you recall from our previous discussions, we said that the optimal epsilon soft policy is the policy with the highest value in each state among all epsilon policies. So it performs generally worse than the optimal greedy deterministic policy pi star. So, but it often performed reasonably well. However, this statement only applies to MDP, not to palm DP setting. So it's not a contradiction from that example we showed. So let's look at more formally. We consider the episodic case where the every episode has every episode ends after a finite number of steps. So for example, chess, Go, these are typical episodic cases. So we would like to optimize the expected value of the start state of each episode with the start state of S0. So the function J theta is our optimization objective. It's defined as the value function V pi for the S on the starting from S0. It's a true value function for a policy pi parameterized by theta. So just to contrast model training in supervised learning versus a policy gradient. So we saw this picture when we discussed the adversarial attacks, where we do a gradient ascent on the input image pixels to maximize the loss function. But here, the picture is a little bit different. So for supervised learning, it's the same. So you are minimizing the expected loss on the training data set by adjusting your parameters to move downhill in the loss function landscape. But for the RL, to maximize the J theta function, we do gradient ascent to update the policy model parameters, the theta, by following the gradient uphill in order to increase J theta. So to avoid the clutter, we omit the subscript and understand that this derivative is respect to the parameters theta. So here's the policy gradient theorem. So we only focus on the episodic case. The continuous case, the derivation process is different, but the final formulas are the same. So here's the derivative. This V pi is the expectation over all the actions for the probability of the action times the Q pi. So this is if you don't remember this, this is our Bellman equation. So taking derivative, you move in the derivative operator, and by the chain rule, you have these two terms. So the policy gradient theorem, assuming discount factor gamma equal 1, says that this derivative is equal to this term. So the mu s is the on-policy distribution under policy pi. And for all the states, it sums to 1. It's a probability distribution. So it denotes the percentage of time spent in state S during all the episodes that you experienced. So a larger mu s denotes state S is visited more frequently. Hence, the policy gradient theorem term for the state S is given more weight. So we care more about frequently visited states than rarely visited states. So here I wrote the proportional to operator, not the equals to. So in the episodic case, the constant of proportionality is the average length of the episode. In the continuous case, it's 1. So in general, it doesn't really matter much in terms of the actual updates to the parameters. So this proof is a little bit non-trivial. So if you look at these formulas closely, so it looks like you threw away this term, didn't you? You have this term left, but in fact, you did not really throw away this term. This is reflected in this distribution over state. So let me just briefly look at this, show you this proof. I won't really go into details. So this is where we stopped. We just wrote this part, product rule of calculus, and then we jumped to the conclusion. But the derivation process goes like this. So you substitute the q pi as expressed in the v pi. This is our Bellman equation. And then the derivative gets rid of the small r term because it's a constant. You have this. And then you substitute, you unroll this this equation because you see derivative v pi on the left, derivative of v pi s prime on the right. So it's a recursive equation. You just substitute the same form into the equation to get this infinite, not infinite, but many unrollings of these terms. And then you express this equation as with the probability of transitioning from state S to state X in k steps. So this derivation says that this because the pi a given s times the p s prime given s and a, if you multiply all the terms for any given state X, then it's the probability of starting from a given state, transitioning to taking a given action A, transitioning to the next state, and then taking another action A prime and transitioning to the next state, and so on. So it's probability of moving into the state X. That's why you can replace that with this single term here. And then this derivative can be expressed as the mu, the eta, which denotes this distribution, a probability distribution, and then you normalize it. Just divide by the total over all the eta to get the mu, the state distribution for all the states. So, so you can see that we're not throwing away any term. So the second term on the right, this guy, is not thrown away is just expressed in a different form by expanding it infinitely many times. It gets folded into the state visitation frequency, the mu term. But anyway, you don't have to know this proof. It's just to show you that I did not really play a dirty trick. So this is indeed a correct formula. You can subtract a baseline from the QPy in the formula, or the baseline BS can be any function that's independent of action A. So subtracting BS does not affect the computed expectation, because if you take these terms, BS times this, no, only this part, and then you can bring the BS out of the summation because it's independent of the action A being summed. So, and then this guy added together is just 1. Actually, there's one more step. You can, sorry, I missed this one step. So you can move the derivative out of the sum, and then the inner sum is just 1. So taking derivative to a constant is just obviously 0. So therefore, you can subtract any baseline function as long as it's independent of the action. So you can subtract it. Subtracting the baseline helps to reduce the variance and speed up convergence. So a common choice of the baseline function is the advantage, the vpi, the state value function. So then you have the advantage function. So it captures the advantage of taking action A in state S, then follow policy pi, compared to the baseline of following the policy pi from state S. So we care more about the relative ranking of different actions in state S, ST, than absolute values of the Q pi SA. So we can subtract this baseline to reduce the variance. It doesn't change the final result. So here's the example of a policy gradient. So so here's the current position of the robot, the agent. Now its policy is to the current policy says move up with pretty high probability, and move down with lower probability, and move left and right with a very small probability. So this is the current policy in the state. And suppose the policy is parameterized by parameters theta. Maybe you have 2 parameters. The theta is 2-dimensional. And then suppose this derivative direction, this is the derivative of the policy function. Suppose it's pointing in this direction, so that is to increase this probability of going left. You must move your parameters in this direction. That is to reduce theta 1 and increase theta 2. So it tells you how to change the policy parameters to make the action left more likely to be selected instead S. So if you perform gradient ascent on theta, we increase this probability of taking action left instead S. So if you move from this point in the parameter space to this point, then the probability of going left will be increased. You have a higher probability of going left now. So obviously, since probabilities add up to 1, the other probabilities are reduced. So here's a example where you have a high reward in the lower right corner, and the current policy is this. So based on the these Q value functions, so so the Q says that going left has a pretty bad outlook, pretty bad Q value function, and going right is pretty good. And going down is also okay. So you can see that the estimate is pretty accurate because it should go right and go down to reach the reward. So after gradient ascent in the parameter space, you should have this new policy like this. So this Q pi is this guy. If you plug in the Q pi into this formula, you get a derivative of your J, the objective, with regard to the parameters theta. So if you do gradient ascent in this direction, then it'll increase the probability. You'll increase these two guys, these two directions, probability of moving in down and right directions, and reduce the probability of moving up or left directions. And among these, moving right will be increased more than moving down, and moving up will be reduced more than moving left. So based on the Q values. So hopefully, after gradient ascent, you should have the new policy like this. So this is how the policy gradient directly updates the policy. So okay, you may ask, this is the Q value function. So if you have this Q value function, so why don't you just take argmax? Why do you just said the policy gradient does not need the value function? Indeed. So this is just a illustration case to show you what happens if you had the accurate Q value functions. In fact, you don't have these. These are not available. You can estimate these with sample-based estimates. We'll show next. So this is the MC reinforced method algorithm. So this is the formula we had before without the baseline. So you can write the sum over all the S over all the experienced states under policy pi, weighted by the visitation frequency with the expectation operator. So after expectation over policy pi is the average over all the experienced states under policy pi. So sample a state ST from all the visited states. And then you do a simple division and multiply. So obviously this doesn't change anything. And then you replace this term as a log, derivative with respect to a log. This is because of this basic calculus formula. And then you convert this guy into expectation over pi. So this expectation over policy pi averages over all experienced actions AT from state ST under policy pi. So by sampling AT from this distribution of the actions from state ST. So whenever we have capital letters, we're referring to a concrete instance that you experienced, a concrete action from a given, from an actual trajectory. Whenever we have small case letters, it indicates a random variable. So these two expectations can be merged because they are both expectations over policy pi. You can write it as a single one. So execute policy pi and average over all experienced states ST and action AT from state ST. So this is the two samples combined into a one operator expectation over pi. And then you can write this guy. Yes?
You're missing right square bracket when you have a double expectation.
Oh, yes, that's a good catch. And then you can rewrite this Q pi SA as expectation over the GT. So the GT return, if you remember, it's the cumulative reward starting from the current step until the end of the episode. So it's an unbiased estimate of the Q pi SDAT. So and this the term in the front derivative with regard to the log pi is called the score function. So once you have this derivative of j theta, you can use a gradient ascent to perform update to the function parameter, to the policy parameters theta, as usual. And also it turns out that if the discount factor, well, our derivation have been assuming this discount factor is 1, but if you had a less than 1 discount factor, you must multiply an additional term in front. So actually this proof is also, it follows from the proof of the policy gradient theorem. If you, that proof assumes gamma equals 1, but if you plug in gamma less than 1, follow this gamma around, it'll show up in here. So here's an example of MC reinforce and show you why you need the log term. So maybe I should discuss the okay. Let's discuss this first. So suppose you have a given state S with 2 possible actions, A1, A2. So initially, the policy is that take action A1 with 90% probability and action A2 with 10% probability. So consider one episode with 9 occurrences of SA1, steps T1, T2, and T9. These may be discontinuous numbers, time instance, or step size, step numbers, and with return of 1. So anytime you take an action A1 from state S, you get a return of 1 after the episode ends. And one occurrence of SA2 at step T10 with return of 2. So assuming alpha equals gamma equal 1 for simplicity, the gradient update is simplified to this equation. So assume that we do not use in-place updates. That is, all updates to theta in one episode does not affect the policy in the current episode. It only affects the policy in the future episodes. So the correct update sequence with the log term is this. So the first update at step T1 is this expression. If you plug in the pi in the denominator, you have this 1 over 0.9 times derivative of pi times the return 1. Second update is the same, except now you have T2, so the policy yeah, so the policy parameters are keep changing. Actually, I think this is not really exact, but let me finish this slide first. So and then at the 10th update at T10, you're taking the action A2. So you have this expression, 1 over 0.1 times this derivative, and then times the 2, the reward. So if you do not have the log, then you have these expressions. So there's no multiply by 1 over the pi. So the correct update sequence gives equal weight to the two action choices with return of 1 with action A1 in state S experienced 9 times, and return of 2 with action A2 in state S experienced once. So if you add up the weights, 1 over 0.9 times 9 is equal to 10, which is equal to 1 over 0.1. So theta will be updated to towards preferring action A2 instead S, because this update has for A2 has a higher G, the return term. So this update should be larger than the combined updates of the first 9 steps. For the incorrect update sequence, it gives 9 times the weight to the action choice with return of 1 than the action choice with return of 2, which is A2, because you're adding up the updates 9 times without the correcting factor. So let me see. Yeah. And then the end result is that the theta will be incorrectly updated towards preferring action A1 instead S. Just because you experienced A1 for many times, you're updating it with a larger weight. That's not reasonable. You shouldn't prefer an action just because it's executed more often. You should prefer it because it leads to a higher return, regardless of how often it's executed. That's why you need this correction term of the log pi term and in the derivative to correct for the execution frequency of different actions. So this is a sentence from the book. The update increases the parameter vector in the direction proportional to the return and inversely proportional to the action probability. So the former makes sense because it causes the parameter to move most in the directions that favor actions that yield the highest return. So you should prefer action A2 because it has a higher return of 2 than action A1 with a return of 1. So the latter makes sense because otherwise actions that are selected frequently are at an advantage. The updates will be more often in their direction and might win out even if they do not yield the highest return. This is this case. So you executed action A1 more often, but you shouldn't wait the updates to a policy of A1 giving it more weight. So you should give it each action equal weight, regardless of their execution frequencies. Oh yeah, so this is why I said here that all updates to theta in one episode does not affect pi a in the current episode. So if you didn't have that assumption, if you have in-place updates, then every step this 0.9 would change. You should the first time it's 0.9 in the denominator, but in the later steps it'll be different every time. So to simplify description, I simply made this a simple assumption so that I can use 1/0.9 in every step. So this is the pseudocode for MC reinforce. So at the end of each episode, you loop over each step of the episode and calculate the return from each time step, and then update the parameter with the SGD, with this expression, with the log pi in the inner within the derivative. So if you don't remember how to calculate the return, let me remind you. This is the value-based IR lecture. This slide. So once you have reached the end of the episode, you simply update each return from back to front for efficient computation with these formulas. So here's an example of a game of Pong. So this is a classic video game that's used by DeepMind in their initial Q learning work, deep Q learning work. So the agent plays one of the paddles. So the other one is controlled by a decent AI and has to bounce the ball past the other player. So for each input image, the agent decides if it wants to move the paddle up or down. You have two discrete actions. At the end of the game, the agent either wins with a +1 reward or loses with a -1 reward. So the rewards are sparse, only at the end of the episode. So so this is a simplifying assumption that you're mapping from the current state to an action, but in practice, in fact, that's what they did. You may stack multiple input images as input to the agent, but it doesn't make too much difference. The agent implements a policy network which maps from input image to two possible actions, up or down, with the stochastic softmax policy. So with the supervised learning, suppose that the neural network predicts y equals up for input x, and it is the correct ground truth label. For example, if you use imitation learning, you have an expert action at every step. Then it's imitation learning is really a form of supervised learning. And then gradient descent will take the neural network more likely to predict y equals up for the input x. So that's a simple case. you have a forward pass to compute the legit, and then you can do a back propagation. Suppose the correct action is up from an expert, you back propagate to update the neural network parameters to make the up more likely. But with RL, if the neural network predicts y equals down for input x, but we don't have the ground truth label in the middle of the game. Unlike imitation learning, we must wait until the end of the game to get a win or lose result. So if the agent loses, then gradient descent will make the neural network less likely to predict y equals down for input x. So suppose this is the -1 here, indicating that the agent has lost the game at the end of the episode. And then you back propagate this information through the neural network and update the parameters to make the down action less probable in all the states. So there's a credit assignment problem that is in the episode of many steps. Which step contributed the most to the final outcome? So if you played a game of 100 steps, maybe one move is really the deciding move that won you the game. The others are just doing nothing. So which one is the contributing factor? So that's a difficult problem in reinforcement learning. So let's plug in the variables for the Pong. On the right corner, I showed the previous slide of the general case of MC reinforce. So for the Pong case, we have two action choices, up or down. So this is the expanded form for the v expressed in pi. And you take a derivative, you get this term corresponding to this guy. So we're looking at a specific state. So we can pretty much ignore the first expectation over the state distribution. And then you do the log trick to get this expression, which is q pi st, which is yeah, this term. And then written in this general form is these two terms. These are equivalent. So suppose that q pi stu is positive, q pi std is negative. So suppose we lost the game for if you take the down action in state st. In this episode, we lost the game. But if you took the up action in the state st, in this episode, the other episode, we won the game. So then if you perform, if you calculate the q pi's, suppose this is the result, and then we know the log pi term is wait, log pi is Oh, the derivative. I forgot this derivative. Sorry. Log. Let me see the update. Alpha. No, I didn't. And then for the up action, the policy update will push. Sorry, I shouldn't assume that. That doesn't mean anything. So for the up action, you should update the parameters with this gradient ascent and push the pi up. Based on this formula, you're moving in the gradient direction of the log pi term, so that this gradient update doesn't matter if it's increase or decrease. In fact, it's a vector of thetas. So some components of theta may increase, some components theta may decrease, but it doesn't matter. What matters is that this particular update will push the pi of up action up. So making it more likely to move up instead of ST. And similarly for the down action. So it'll make it less likely to move down instead of ST. So the Q pi STD is negative. So this is gradient descent with a negative term in here. So gradient ascent turns into gradient descent. So suppose the agent plays 4 rollout episodes and won 2 episodes and lost 2 episodes. Assume each episode lasts 200 steps. So agent made 200 decisions of up or down in each episode. So suppose each step has reward of 0. So we don't care how long each episode lasts, as long as we don't only care about the final outcome of the game. So, and for simplicity, we assume the discount factor gamma is 1. So therefore, for all times, the return is just equal to the final reward, the win or lose result. So return at any time step t is equal to the reward at the end of each episode, because of these 2 conditions. RT is 0 and gamma equal 1. So for each of the 2 winning episodes, for all t, GT is positive. The neural network parameters are updated to encourage all taking actions in the 200 steps to push up the probability of the action AT given ST in this trace in the trajectory of the state action reward. And for each of the 2 losing episodes, you update the parameters to discourage all taking actions in the 200 steps. You push down the pi for the particular action in every step. So now the neural network will become slightly more likely to repeat actions that worked and slightly less likely to repeat actions that didn't work. So for each of the actions in the winning episode, you push up your probabilities in the policy function. In every of the losing episodes, you push down the probability. So as you can see, we're not doing quality assignment really. So we're pretty much saying that if you win an episode, all the actions are good. If you lose the episode, all the actions are bad. So obviously this is very simplistic, but if you average the result over millions of episodes, it actually turns out to be pretty good. So so this is the case for RT equals 0. So suppose each step has a reward of -1 to minimize the length of each episode. So we may prefer a short losing episode to a long winning episode. And suppose the discount factor gamma is 1, and we have these two episodes. In one long episode, we have a reward of the winning episode of reward of 2. And for the losing episode, we have a reward of -2. And then the return can be computed with this. So the return gradually becomes more and more negative near the beginning of the episode, because the episode is becoming longer. So the reward of -1 each step costs you a lot. So that's from the G return, you can see that we should really prefer this loose trajectory than the win trajectory in the state, in this particular state. So the state is a collection of pixels. So after the winning episode, the neural network parameters are updated to discourage the up action in state ST. So in this particular state, this up action is pushed down. The probability is pushed down. And after the losing episode, this probability is pushed up for the down action. Push losing episode, discourage. Yeah, push down. Sorry, both are negative. So, however, since the return of -6 is more negative than -5, the first update, this guy, will push down the probability of up action more than you push down the probability of the down action. So agent is slightly more likely to select the down action in state ST. So that's why you need the baseline. So subtracting a baseline, for example, subtracting the value function for state ST to replace GT helps to reduce the variance and speed up convergence. So suppose you subtract a baseline of -5.5, then updates to theta will be in two different directions for the two episodes. One is positive, one is negative. But in this case, both are negative, but their magnitudes are different. So on the course homepage, I came across this video.
Here's the action,
Which is by this Luis Serrano is my favorite YouTuber. So he does tutorials on machine learning, which are very easy to understand. So in this example, he gave a grid word example where the agent is trying to reach a high reward and avoid this bad state of -1 reward. So we have 4 actions in each state. And in this case, the gain, the return is are computed like this. So 4, 3, 2, 1, 0, -1, and so on, because every step has a cost of -1. So for the positive gain steps, you push up the probability of the action taken in that step. So increase the log loss to increase the probability of that particular action in the episode. And for the negative terms, you decrease the probability of taking that action. So in fact, I wrote this comment to him. That's me. So your description of policy gradient is not very complete. So the specific path is actually the shortest path to the goal. So this path from the state here is actually the shortest path. So why would you decrease the probability of taking the actions close to the beginning of the episode? It still works because for any other episodes with longer paths to the goal, the probability of other actions will be decreased even more. So you can subtract the baseline from the return to speed up convergence. So all actions in the shortest path will have positive updates in their probability. So any questions? So there are several variants of policy gradients. So this is the MC reinforce. It has no bias because you're getting the ground truth return from the term at the end of the episode. It has high variance because the episodes may be very long, so that every time you update, you may update to a very different direction with very different magnitudes. So so the variance is large, which means that convergence is slow. For MC reinforced with a baseline, you can subtract this estimated state value function to reduce the variance. So this V pi hat is the function approximation of the true V pi. So all the true V pi and Q pi terms, they're not available in the during the training process. So you must perform estimation. I will show how we do the estimation in the Actor-Critic method. So for the Actor-Critic method, you use this delta t term. So there are two versions of Actor-Critic. One is Q Actor-Critic, where you this is the expression. This is the sample-based estimate of the action value function Q pi. Or advantage Actor-Critic is the sample-based estimate of the advantage function Q pi SA minus V pi. So this is called A to C. So MC reinforced is a special case of A to C. So suppose your episode is this. So you have many steps. All the way to the end. And end of the episode is the nth step. This is the current step. There should be T, capital T. So for the MC target, you're waiting until the end of the episode and computing the return. So you have the ground truth return. So for the one step TD, you're looking at one step to T plus 1 to get your TD target, and then subtract the current estimate to be the TD error. But you can do a multi-step TD target where you add up the reward of M steps. So you look at M steps, and then you add this V pi at the T plus M. So obviously, if the M is equal to capital T, you're looking at all the way to the end of the episode. So that's why reinforce is a special case of A to C. with very large M for the M-step TD target. So if you get confused, I just added a slide here this morning. So the trajectory is this set of traces, STR. So the convention is that the reward is from state ST, action AT is the RT plus 1. So this is the convention used in the textbook. Other people may say ST, AT, RT. So it's equivalent. It's just a difference in indexing. So suppose we use this convention, then the return is this expression. Written in summation form is this. And that's why this expectation over pi the GT is equal to Q pi ST80. So you're summing the reward starting from here. So it's the same as taking action AT in state ST and then summing the future rewards, all the future rewards. And this tool just reminds you how to compute the target for the TD updates. So this is the TD update for the pi, and this is the target for the TD update for the Q. And these two correspond to, so this expression corresponds to the Q actor critique. And this expression corresponds to the advantage actor critique. So it's actually a sample-based estimate of the advantage function. So this is the one-step A to C. Where so yeah, so first you compute the TD error, and then use the TD error in updating both the critique parameters W and also the actor parameters theta. So the critique parameter update is based on least squares minimization we just showed in the last lecture. So at every step, take action AT in state ST, compute TD error, the critique compute TD error with the value function here, and update its parameters with semi-gradient TD0. And actor updates its parameter with the policy gradient. So if delta t, the TD error is higher, it's a positive, then it means that AT resulted in a higher one-step estimate of the value than the expected V hat. So that probability of AT in state ST is increased. That is, you're taking action AT in state ST, and you get a pleasant surprise that the reward looking at one step is higher than the expected reward you thought it should be. So you should encourage that action, and vice versa. And actor and critique learn at the same time, constantly interacting. The actor is continually changing the policy parameters theta to exceed the expectation of the critique, and the critique is constantly updating its value function parameters W to evaluate the actor's changing policy more accurately. so that the problem is interactive learning between the actor and the critique, because the policy parameters are changing constantly, and the policy is changing. So the value function for that policy, the parameterization W, should also change along with the policy. So these two are really in a intricate dance, and updating, interacting with each other, as opposed to Monte Carlo methods, where you're performing updates at the end of the episode, which is much more static. So if you use neural networks, you may say this is a video game, and you may have a critique that extracts a value function, a value from a input image pixel collection of pixels, and the actor has a policy network that maps from the input image into a set of action probabilities with a softmax. And then you can see that both of these networks require a convolutional network to extract features from the input. So you may share these convolutional layers to have a single network with two heads. One head computing the action probabilities as the policy network, the other computing the value function estimates with a regression head. So advantage actor asynchronous advantage actor critique is A3C is to implement parallel training with so-called asynchronous updates, where multiple workers in parallel environments independently update the global value and policy networks for effective and efficient exploration of the state space. So you can parallelize the training process over hundreds of GPUs, which may make the convergence much faster. So we have been discussing discrete actions with the softmax parameterization of their probability of taking each action, but sometimes continuous actions are preferable. So it may not be straightforward to choose a proper discrete set of actions, and continuous actions allow us to generalize over actions. So here shows a probability density of the continuous action range. Could be a steering angle, it could be acceleration forward in the forward direction. So if an action is good, its neighboring actions are also likely to be good. So discrete actions lack generalization. So each action is independent of others, including its neighbors. So similar to value functions for discrete states. So if you learn that taking the action, suppose you have a set of discrete actions. In a grid world, you have maybe, so 4 is one choice, 4 directions, or you may have 8 directions to be more fine-grained. So, or you may have more. So suppose you learned that this direction, east direction, is very good. So you should increase the probability of going east. Then in a reasonable environment, the northeast and southeast directions should also be increased because they're moving in a general direction. So if one is good, it implies, not always, but most often, that these two are also good. However, for a discrete set of actions, these actions are all independent. And if you update the parameters for going east, it doesn't really affect the other two actions. And that's not good. That's lack of generalization. But if you had a continuous variable indicating the direction of a movement, then it has generalization, because the neural network or some other function is continuous. So moving east, if the east direction is good, the function will be updated so that any direction in the general direction of east will be also be good, will be also be increased in their probability. So a Gaussian policy is a very common choice for parameterizing the continuous actions. So a Gaussian looks like this. It has two parameters. The mu is the mean, the most likely action, and the variance, sigma squared, controls the degree of exploration. A flatter Gaussian with a larger sigma has more exploration. So initially, you start from a pretty flat Gaussian with a pretty random policy to encourage exploration. And then as you learn the policy parameters, gradually the Gaussian becomes narrower and variance is reduced during learning with policy gradient. Now finally, at the end, you should converge towards a deterministic policy, or you may leave some non-determinism in the policy. So that's the end of the policy gradient lecture. So there's the last lecture. I don't have. Oh, sorry. Did I mess up the name? Oh yeah. So I'll fix it. So I don't have time to give the lectures, but in the last year's lectures, I had this week 6 and week 7. These two are discussing that PowerPoint on the homepage. So it really is autonomous driving with imitation learning and reinforcement learning. And this is a paper. It's DRL in autonomous driving, a survey. So that's pretty much it for today. So as I mentioned in the announcement, we're gonna have a Q&A session. Oh, there's a question here. So how many questions will it be? I have the 2.5 hours set up for the exam. So the number of questions should be around maybe 40. Yeah, I'm still giving the questions. I haven't finished yet. But the last question, it should be similar to the ones in the worked examples, but with a much lower complexity. So you can finish it in time. So on Friday, you can bring your questions, or we can just have some informal discussions on anything related to the course. So I thought of giving a review lecture, but since we covered so many materials, I can't really do justice to the course material in a 2-hour review. So I thought maybe we'll just have a Q&A session. So any questions on the policy-based IR? Yeah, so in reality, in both for autonomous driving, especially both value-based and policy-based are used very pretty much equally. So both are very popular. So let me see. Yeah, I got some requests from students requesting the extension for the lab 3. I wonder if it's necessary. We have received a few submissions, but so what do you think? Have you finished lab 3, or do you plan to finish it in time?
I can start. I haven't finished, and I'll try to finish it. But, so.
Yeah. So we'll see. We'll see. So the deadline is pretty close. Okay. Yeah. Okay. We'll see. If you get too few submissions and many requests for extension, I may give an extension, but yeah. Okay, that's it for today. Thanks for sticking with me for so long. Yeah, okay.
So.
Goodbye. Good night.
Oh, thank you. Bye.
Sure.